We are going to cover section 4.5 today. So this is going to cover exponential and logarithm equations. So this is basically exponential and logarithm equations. So first we're going to start with how to solve some exponential equations. Then after we do a couple of those, we'll go over to how to do some logarithm equations. And then that should wrap the section up. Um, First of all, what we're going to be using in these is if I have, say, an exponential equation, like let's say 3 to the x equals 11, what we want to do is we want to use those inverse properties. If you remember from 4.1, if you guys have an exponential, its inverse is a logarithm of the same base. And if you have a logarithm of a base, its inverse is an exponential of the same base. So to solve this type of problem, what we're going to do is we're going to apply logarithm base 3 to both sides of the equation. Then the logarithm base 3 will undo the exponential base 3. We'll get x is log base 3 of 11. And the homework's going to ask you guys to round these to like 3 or 4 decimal places. The problem is those little scientific calculators, they don't have a log base 3 button. So we're going to use that change of base formula to convert these over to a button we do have, which is natural log. So it'll be natural log of the parentheses stuff over natural log of the old base. That's equal to log base 3 of 11. So we'll just type into our calculator, what is natural log of 11 divided by natural log of 3? And we'll round this to, say, 4 decimal places. It'll be 2.18. It's 265, so we'll say 27. So that's about equal to that. So the idea with these is basically get the exponential part by itself first, apply a logarithm of the same base, and then you convert over to natural log so you can type it into your calculator. So let's take a look at another kind of simple case, and then we'll look at some kind of weird stuff. So let's say this time we have 8 to the x minus 3 plus 2 equals 10. Or let's say 15. So 8 to the x minus 3 plus 2 equals 15. First, we need to get the exponential part by itself, so I need to subtract the 2 across. So we get 8 to the x minus 3 equals 15 minus 2 is 13. And now what I want to do is I want to apply log base 8 to both sides of the equation, so I match the base of my logarithm. I match my logarithm base to the exponential base. These are inverse functions, so they'll undo each other there. And we'll get x minus 3 equals log base 8 of 13. And then I just need to add the 3 across to get my x. So x is log base 8 of 13 plus 3. Again, if we want to type that into our calculator, it's natural log of the parentheses part 13 divided by natural log of the old base 8 plus 3. So I'm rewritten the log base 8 of 13. I rewrote it in this form so I could type it into my calculator. And we'll round this to like 3 or 4 decimal places. So natural log of 13 divided by natural log of 8 plus 3 is 4.2335. And that's our answer. So most of the initial exponential stuff, you solve it like this. It's pretty easy. Get the exponential part by itself, apply the matching logarithm to both sides, then convert over so you can type it into your calculator. And that's those initial ones. So let's look at a couple of kind of weird things. Let's say we had 7 to the x equals negative 4. Well, if you guys have an exponential equals a negative like this, 7 to the x is a exponential. Its graph always stays above the x-axis. If we graph 7 to the x, it actually crosses here at 1, 1. Then at x equals 1, the y value is up here at 7. So it's a exponential curve that goes up pretty steep. And it approaches the x-axis asymptotically, so it never gets below the x-axis. So this has no solution. Or you could say the solution set is the empty set. So if you guys have something like that, or maybe have a fractional base, 1/4 to the x equals -3, the solution set is empty. You guys have to have the exponential part by itself over here to make this thing. If you had something like, let's say we had 3 to the x minus 7 equal -2. We can't immediately say if this has a solution or doesn't have a solution because we don't have the exponential part here isolated. So even though this is equal to a -2, we have to get the exponential part by itself first. So if we add 7 across, then we see, well, it's 3 to the x equals, it's actually 5. And this one is okay to solve. So just because you see a negative off to the right-hand side, the only way you can jump to these types and say that the solution set's empty is if your exponential part's by itself over here. If you got some other stuff, like in this case, you need to get the exponential by itself. And then let's just solve this one out to finish things out. We could say, well, match log base 3 to get rid of the exponential base 3. And then we get x is log base 3 of 5. So again, that would be natural log of 5 over natural log of 3. So natural log of the parentheses stuff over natural log of the old base. So natural log of 5 divided by natural log of 3 is 1.46. We'll say 5. Round it to 3 decimal places, I guess that one. The homework asks you guys to round to 4 or 3 decimal places sometimes, depending on the problem. So just make sure you're reading them carefully and rounding them to the amount they say. Okay, so the last case with exponential equations. And this is where stuff gets a little weird on these types. Suppose we had 8 to the x minus 2 equals 5 to the 4x plus 1. So we can't really, since there's two different exponentials, we can't really match the base. If we match base 8, then it doesn't cancel base 5. If we match base 5, we don't cancel base 8. So we kind of have this problem of I can't get rid of both my exponential parts. So in this case, what we do is we say, well, we can't use the match the log trick. So we're going to apply a logarithm that at least is a button that we have on our calculator. So we're going to apply natural log to both sides of the equation. Now, if you guys think back to logarithms, we had that property that said powers are able to pull out front of the logarithm that they were inside. So this will get us x minus 2 times natural log of 8 equals 4x plus 1 times natural log of 5. So I just push the powers out front using that third property of logarithms from, I think, section 4.3. So now I need this natural log of 8 to distribute to get rid of these parentheses here so I can get at the x. And I need the natural log of 5 to also distribute to get rid of the parentheses to get at its x. So I have x times natural log of 8 minus 2 times natural log of 8 equals 4x times natural log of 5 plus 1 times natural log of 5 is just natural log of 5. Okay, so on these types, when people start solving them, this is usually where we get stuck and we're not sure what to do. What y'all need to do is get all the x terms on one side. So I'm going to subtract my 4x natural log of 5 term across that way. And then my term that doesn't have an x, I need to push it back across the equal sign. So I will have x natural log of 8 minus 4x times natural log of 5 equals, now this negative 2 natural log of 8 is going to add across, so it'll be a positive 2 natural log of 8 plus a natural log of 5. So what I have to do now is factor out the x, The left-hand terms each have an x, so we factor the x out. So we get x times natural log of 8 minus 4 natural log of 5 equals 2 natural log of 8 plus natural log of 5. And then to get the x by itself, it's x times this natural log of 8 minus 4 natural log of 5. That's separated from x by a multiply, so we just have to divide it across. So your answers on these are going to be kind of messy. They're going to have a lot of stuff going on. But since we use natural log, that will be a button you have on your calculator. So we're going to just take this and let's round to 3 decimal places this time. So I need to just type this in my calculator carefully. So I get 2 natural log of 8 plus natural log of 5. That whole mess divided by natural log of 8 minus 4 natural log of 5. And if I've typed this all in, we said round to 3 decimal places this time, we get a negative 1.324. And again, in the homework parts from these exponentials, the book asks you guys to round to 4 decimal places sometimes, and sometimes 3 decimal places. So that is how you guys handle the types that start out with 2 different bases. You apply natural log, pull the powers out front, then distribute and get the x by itself. Okay, so that does it for exponentials. Now we need to do the reverse, and we need to cover logarithms. Unfortunately, with logarithms, for logarithm equations, you need to check answers. So sometimes you guys get an answer, and you plug it back in, and it doesn't work. So this section, we need to be a little bit careful about that. Okay, so we're going to go through, and we're going to solve some of these, and go from there. So our first one we'll take a look at is, what if we have the log equation for natural log of x equals 12? So the first thing I'm going to do is divide the 4 across. 12 divided by 4 is 3. So I get natural log of x equals 3. We want to remember natural log is base e. So if I raise both sides to exponential base e, what I get is, this cancels, I get x is e cubed. So we say, okay, that seems, when we leave our answers like this is called exact form. So exact form, I should say that also. Let me go back to, well, let's finish this one off, then I'll say it back on the exponentials. So exact form is the form you guys have before you put it in the calculator. If I wanted to round this to a decimal place, we could say like e to the 3rd power. That would actually be about equal to 20.086. So this is it. This is it rounded to some decimal places. Exact form is the form that you type into the calculator. So we need to check our answer on this. Then I'm going to scroll back up, and we're going to just take a look at some other exact forms. So to check our answers, we'll say, all right, you have to start with the original form of the equation, replace the x with what you got. Now, natural log and exponential base e are inverses, so they undo each other. You get 4 times 3, because the 3 is left behind after the natural log and e undo each other, equals 12. And yes, that's good. 4 times 3 equals 12. So we have our x is e to the 3rd. Going back up, exact form on some of these exponential equations we solved. This right here would be the exact form for that example. Up a little bit further, this we could say is the exact form. This right here also would be exact form. I'm not sure on the exact forms, the homework system, if it asks for exact form, I'd try it with the natural logs and just see if it likes that. And if it doesn't, then I'd go back to the base 3. But I'm pretty sure it's defaulted for natural logs. So like on this one, here's exact forms. So the exact form is basically the form you guys have. before you put it into the calculator, and then you can get a decimal approximation. So when they ask you guys for exact form on some of these, it's the form that you guys have that you would then type into the calculator. Okay, so we're going to do a couple more of these logarithm types. Let's say we have log base 3 of 4x minus 5 plus 1 equals 3. So just like with the exponential types, you need to get the logarithm by itself first. So we're going to subtract the 1 across, and we're going to note, so this is 4x minus 5. 3 minus 1 is 2, so we get it down here that this equals 2. So step 1, get the logarithm by itself. Then you can plug stuff in and see what happens. We need to undo logarithm base 3, so I'm going to apply exponential base 3 to both sides of the equation. This will undo the logarithm base 3. I'll get 4x minus 5 equals 3 squared is 9. So then we will add the 5 across. So 4x is, see, 9 plus 5 is 14. So x is 14 over 4, which is, divide them both by 2, that's 7 halves. Okay, so we think we have our answer here. To check it, we're going to plug back into the original form. And we're going to see, does the original form with 7 halves replacing the x, does that actually end up being 3? So let's see here. The 2 here can cancel with the 4. That'll leave a 2 up there. 2 times 7 is 14. So you have log base 3 of 14 minus 5 plus 1 is 3. That's what we're trying to check. So we say, okay, 14 minus 5, that's 9. So we got log base 3 of 9 plus 1 is 3. So we got to think 3 raised to what power makes the 9? That's what this logarithm here is represented by. So this logarithm term here, we think 3 to what power? What power do I raise the base to get the thing in parentheses? Well, 3 squared is 9, so log base 3 of 9 is really 2, because that says raise the base 3 to the second power to get the thing in parentheses. And we get 2 plus 1 is 3, and yeah, sure, that's good. So since that works out, our answer checks out, and we have our solution. You do need to check your answers on these. So that's kind of the annoying part about this stuff is you have to go back after you do all the work. You have to go back and in the original form verify that your work makes sense and that everything's working out okay. All right, so we got just I think 3 more examples to get through. Then that's this section. So what if we have a type like this where we have common log of 3x plus 2 plus common log of x minus 1 equals 1. So when you guys have multiple logarithms, you have to use those properties of logarithms we did back in section 4.3 to combine them together. So when you have 2 logarithms of the same base and they're separated by an addition, you combine them as a single logarithm with the 2 parts that were inside the original logarithms multiplied together. So now I've got this down. So it's log of this first part plus log of the second part. That's log of the first part times the second part. Remember, this is common log, so it's base 10. So at this point, I've got the common log by itself. There's only one term. It's common log. So I can raise both sides to exponential base 10. That'll undo the logarithm. Then I just need to FOIL out the inner stuff. And so I get 3x times x is 3x squared minus 3x plus 2x minus 2. And that equals 10 to the first power, which is 10. So from here, I just need to solve my problem. So let's see here. We got 3x squared minus 3x plus 2x is a negative x. The 10 is going to subtract across as a negative 10, so that'll make it a negative 12 equals 0. So, let's see. I'm not sure if that factors or not, so I'm going to the quadratic formula at this point. So x is negative b plus or minus the square root of b squared minus 4 times a, which is 3, times c, which is negative 12. All that over 2 times a. Okay. So x is 1 plus or minus the square root of, let's see what's going on here. Negative 1 squared is positive 1 plus, this is negative 12 times negative 12 is positive 144. So that's 145 over 6. So I have x is 1 plus square root of 145 over 6, or x is 1 minus square root of 145 over 6. Okay, so let's check these. I'm going to use my calculator to check this because when we plug those values into this is going to be pretty annoying to check. So I'm going to plug 1 plus square root of 145, all that divided by 6 in for x there. And I'm going to plug in 1 plus square root of 145, all that divided by 6 in for there. This is kind of a messy thing. I guess let's do it. Maybe let's pull up. Let's just do it real quick and see what we get. So I'm typing in my calculator. We get 3 times 1 plus square root of 145. Divide that by 6. And then that all gets added by 2. And then we get plus common log of, let's see, what is this? 1 plus square root of 145. Divide that by 6. Minus 1. And this ends up equaling 1. So when I put those in there, when I plug that in, the calculator returns 1, which is what it's supposed to equal. So 1 plus square root of 145 over 6. That one works out good. That's one solution. So this one checks out, works out okay. So I'm going to go through and say, well, what if instead of pluses, what if we changed those pluses in these things? What if we scribbled that out and made them minuses? So what if we scribbled those out and we did the 1 minus square root of 145? So if I go back and change the pluses in these to minuses, so we can see what's going on, I get non-real answer, which means I probably took a logarithm of a negative, so the 1 minus square root of 145 over 6. This one doesn't work. The calculator returns a non-real solution. So this is a reason we got to check our answers. Sometimes they both work. Sometimes one works, the other doesn't. Sometimes neither of them work. So here the positive solution was okay. The negative one didn't work. Okay. We got 2 more examples to do. So let's say we had common log of x plus 6 minus common log of x plus 2 equals common log of just x. Okay, so step 1, we need to combine the left-hand side, get it down to a single logarithm. This time it's a subtraction. Subtractions combine back as divisions, where the term that had the negative sign is the term that goes down below. Now these are both common logs, so we're going to raise both sides to exponential base 10. And we get a nice thing that happens here where, since they're both common logs, when you raise them both to exponential base 10, they both cancel. So we get x plus 6 over x plus 2 equals x. I'll multiply the x plus 2 on up. Okay, so now I got to distribute my x. So my x distributes. I get x plus 6 equals x squared plus 2x. I'm going to subtract the x across and subtract the 6 across, trying to get everybody on the same side so I can factor or quadratic formula. Let's see, so that's going to be a plus x minus 6. Okay, so I need two numbers that multiply together to be 6, but could add up to be positive 1, which will be a positive 3 and a negative 2. So x is negative 3 or x is positive 2. So we have to check, is x negative 3 or x positive 2? Do these work? Well, so I got to go back to my original form, and I'm going to check x is negative 3. So I get common log of negative 3 plus 6 minus common log of negative 3 plus 2 equals common log of negative 3. Now, you can't take a logarithm of a negative number, so like negative 3 plus 2 becomes negative 1, and that would have us taking negative common log of negative 1. Log of negative 3 is bad, so this whole term here, this doesn't work. So we can just say no logs, it's log of any base, no logs of negatives. So that's causing the issue, is we had a logarithm of a negative number. Now, just because you get a negative number here, you have to actually plug it back in, because like, negative 3 plus 6, that's positive 3, so that first logarithm's actually okay. So just because you get a negative answer, you can't immediately just throw it out and say it doesn't work. You gotta plug it in and then see, well, if this was like, x plus 6, and this was x plus 9, and this was x plus 4, and we got negative 3 back, when we plugged them in, it would just be logarithms of positive, so it would be okay. So I'm saying just because you get a negative solution doesn't mean you can automatically throw it out. All right, let's try x equals 2. We want log of 2 plus 6 minus log of 2 plus 2 equals log of 2. So 2 plus 6 is 8, so this is common log of 8 minus common log of 4 is that common log of 2. Well, now that we've verified that these logarithms make sense and that they're both logarithms of positive numbers, we can combine this as logarithm of 8 divided by 4. And does that equal logarithm of 2? And sure, since 8 divided by 4 is 2, this is log of 2 equals log of 2. So this right here, everything's good and checks out there. Our solution makes sense. Okay, let's look at the final one here from this section, then say that that's good enough. And we got, what do we got? Okay. So we say we want to find the time needed for $4,000 to grow to $5,000 at, we'll say, 3% compounded monthly. So we're using that present value, future value equation again. And this time we're trying to figure out what's the time. So they gave us the equation A equals P times 1 plus R over N to the N times T. And our goal is basically get the T by itself this time. So A is the future value, so that's the $5,000 we want the $4,000 to grow into. P is the $4,000, that's our starting value. Interest rate's 3% as a decimal, so that's 0.03. N is 12, the number of times we compound. Since we're compounding monthly, N is 12. And we get our equation looking like this. So we want to solve this. So I'm going to divide the 4,000 across. So I get 5,000 divided by 4,000, which is 5/4, equals, let's see, what is this decimal? So I want to know what's 1 plus 0.03 divided by 12. And that is 1.0025 to the 12t. So this turns into a nice little exponential equation we want to get rid of the exponential base 1.0025, so I have to apply a logarithm of the same base to both sides of the equation. And when I do that, the logarithm base 1.0025 undoes the exponential base 1.0025, and we get log base 1.0025 of 5/4 equals 12 times t. So to solve this, we just need to divide the 12 across. I also need to convert this over to a form I can put in my calculator, so I'm going to do natural log of the top part over natural log of the bottom part, natural log of the parentheses stuff over natural log of the old base. And then we want to divide the 12 across. And to avoid a triple fraction, instead of dividing by 12, I'm going to multiply by 1/12. I can multiply 1/12 by 12, and that'll undo it. And it just, you could write this all and then divide that all by 12, and it turns into like a triple fraction looking thing. But I want to do it this way just to keep stuff looking a little bit cleaner. Let's see. And then we're just going to take this and this is years, so we'll round it to like 2 decimal places. So again, this right here that I got right now is exact form. So this is exact form. So that's exact form. And whatever I type in my calculator, because I don't really have a good feel for how many years that actually is. Type that all in our calculator, and it's 7.45 years approximately. So if you put that in your calculator, that'll say that's about how long it takes for that to work. So that should be enough stuff to do your homeworks, and that is section 4.5.